Welcome to our final video lesson on the unit regarding quadratics. We're going to take what we've learned about quadratic equations and functions and kind of put it all together into some applications. We're going to start with a couple of just quick little additions. We're going to talk about the nature of roots. We're going to look at how to generate quadratic equations, and then we're going to take that knowledge and we're going to put it all to play in some application type problems. All right, so let's get started first with this slide that I've got here. So it talks about being able to determine the number of zeros, which means roots or solutions, that a quadratic equation has if it's presented in vertex form. So someone makes the claim, Randy makes the claim, that he can predict whether a quadratic function will have 0, 1, or 2 zeros if the function is expressed in vertex form. And it says, how can you show that he is correct? Well, think about vertex form. So if I had a quadratic and I knew that it looked like this, I would know right away it has no solutions, or no zeros. And you may say, how do you know that? Remember the connection between zeros, roots, quadratics. What you're finding is where does that quadratic function, the corresponding function, where's it cross the x-axis if you took the function and set it equal to 0. This doesn't, so that's why I would know it has none. So if you know the vertex is above the x-axis and it opens up, there's no solutions. So let's look at the three possibilities down here. So here's a quadratic. So I can tell that the vertex is at 2, -5. I can tell that it opens up from the knowledge I've gained of quadratic functions because the stretch factor in front is a positive. So if the vertex is at 2, -5, picture, there's 2, -5 down here. It opens up. Well, it's got to cross the x-axis twice then because the vertex is below the x-axis. So this would be an example where the quadratic has to have 2 possible solutions, which was right. So if we go down to the next one, so we have 3 of them here. So this one is just the old standard base parabola f of x equals x squared. Well, we know that that looks like this. You can see, I guess down here in the one drawing, it's right there. Its vertex is at the origin, 0, 0. So if I said to you, well, how many times does that graph cross the x-axis? Your answer would be only once. And the reason I knew that is because the vertex was right on the x-axis. So if the vertex ends up right on the x-axis, that means you're only going to have the one x-intercept, which means you'll only have one solution or 1, 0. And then, of course, the one I've already mentioned. We look at this final one. So now your vertex is at -3 and 4, which puts it above the x-axis. It's also going to open up because of the positive stretch factor. So if you have -3 and 4 vertex and it opens up, that quadratic or parabola is never going to cross the x-axis. So this quadratic, if you were to set it equal to 0, it would have no solutions because of the orientation of the vertex and the way that the parabola opens. So there's an actual kind of technical name for what we're talking about here, and it's referred to as the nature of the roots. And the way that it's looked at is by examining the quadratic formula. So if you think of -b plus or minus the square root of b squared, subtract 4ac. So we looked at this formula in our last video, divided by 2a. And it's determined that this quantity here, underneath that square root sign, it is the determining factor in whether you get one solution, 2 solutions, or no solutions. So why is that? Well, I want you to think about, if you had the formula, x equals, and let's put some numbers in. Let's say it was -3 plus or minus, and let's say you had a 2 down here. Let's look at the importance of this number. If you took -3 and you added or subtracted some number to it, that's going to guarantee that you're going to get two different answers. Because if you took negative 3 and add a number, then you took negative 3 and took away that number, well, you're going to get two different answers, which means that's going to give you, when you divide by 2, you're going to get two different solutions. So if you get any positive number here, you have to get two answers. Well, the only way to get one answer would be if this number was a 0, because if you went negative 3 plus 0, and negative 3 take away 0, that's the only way you get the same answer both times. So in that situation, if you went negative 3 plus 0 and divide by 2, and then negative 3 take away 0 and divide by 2, you're going to get the same answer. So that means, now sometimes they say two, rather than saying one answer, sometimes they'll refer to it as two equal solutions, meaning you get the same answer both times. And then the third situation, where you get no solutions, would be the situation where underneath here is a negative value, meaning you can't even take the square root of it, so you don't even, it's impossible to get a number here. And when that happens, we say there are no possible solutions. And to clarify that, there's no possible solutions in what are called the real number system. There is another number system called the complex numbers or the imaginary numbers, which would extend and allow you to take the square roots of negative numbers, and we haven't looked at that yet. So if you see them referring to the imaginary number system, which they're going to talk about down here in the descriptors we use, what they mean, that's what they mean, is that in the real number system, you can't take the square roots of negative numbers. However, if you did extend into what's referred to as the imaginary or complex numbers, you could in fact take the square root of a negative number. Okay, so to make our discussion flow along here, the part under the square root sign, not including the square root, just the b squared minus 4ac in the quadratic form has a special name. It is called the discriminant. And it is found that if you just figure out the value of the discriminant, you should be able to figure out how many answers you're going to get for that quadratic. Now, not what the answers are, but the discriminant itself will tell you how many answers you're going to get. And it's kind of laid out down here below. So if you figure out the discriminant and you get any positive number, that means you're going to get two distinct, which means different, real solutions. So they're going to be in the real number system. If your discriminant turns out to be 0, I'm just going to put a little picture beside them. So in this scenario, it's indicating, right, in order for the discriminant to be some positive number, visually, that means your quadratics crossing the axis twice. 1, 2, two answers. If your discriminant turns out to be 0, it's got to be this situation, just touching the axis once. That's how you get one real root. See how they refer to it as a double root? The reason they're calling it a double root, remember I showed you in the quadratic form that if you went up here above, negative 3, right, negative 3 plus 0 divided by 2, and then negative 3 minus 0 divided by 2, both of those, you're getting the same answer. So that's what they mean when they say a double root. And finally, if this value was a negative number, that would mean that under here you're getting some negative number. You can't take the square root of a negative number, which means you get two imaginary roots. That's what I was talking about. So often too they'll say no solutions. It's another descriptor for it. Now when I say no solutions, what I mean by that is no solutions in what are called the real numbers. As I said, they can also be referred to as imaginary roots, or another one is they're also called complex roots. Complex numbers and imaginary numbers are interchangeable. Okay, so let's have a look at these three diagrams. So if I looked at each of these three diagrams, you should be able to tell me the sign of the discriminant and how many and the nature of the root. So just kind of describe what's going on. So this one, as soon as I see this, it's never crossing the x-axis. That means the discriminant, I'm just going to use capital D, is got to be negative, less than 0, which means I have no real solutions. So now I'm describing the nature. The nature, I mean, what kind of answers are you going to get? So you may say, I'm going to get two imaginary roots. I don't like to use that too much because you don't really know what I even mean by that, but just trust me when I say there is another number system that would extend and allow you to take the square roots of negative numbers. So I look at the second one, and I notice that I'm getting just the one answer. So the only way you can possibly get one answer is if the discriminant is exactly 0. That tells me that I'm going to get only one real solution. And finally, we have a quadratic that's crossing the x-axis in two different locations. That could only possibly happen if the discriminant is a positive number greater than 0. And that means that I'm going to get, so this describes the nature now, so I'm going to get two real, sometimes they'll refer to them as distinct just to tell people that they're different. Unique is another word that I've seen used before, but they're two different possible answers. Now, if I just go back and look at that real quick, there is one other further classification that you can make. We talked about it actually when we did the quadratic formula. It would be kind of a special case of the positive version. And if I said to you, what if D was equal to a perfect square? Would that make any difference? So if underneath here, this value was a perfect square, well, from our work on solving quadratics using the quadratic formula, we revealed that if that turned out to be a perfect square, then the quadratic actually would have factored. And if a quadratic would factor, you get nice rational number solutions. Versus if it's not a perfect square, you're guaranteed to get irrational, sometimes we'll call them ugly answers, meaning they're non-terminating, non-repeating decimals, because any radical that's not a perfect square is, by definition, irrational. So that would allow you to further classify whether your answers are rational or irrational here. So if it's a perfect square, we can furthermore say that my solutions are rational numbers. Versus a non-perfect square, still positive, but not a perfect square. So for example, let's say here the discriminant would have to be something like 25. Then I know the answers are rational. Let's suppose the discriminant was just 10. Well, 10 is not a perfect square. So if 10 is not a perfect square, that means that underneath that square root sign, I wouldn't be able to get a single exact value. And this would still be two solutions, but they would be irrational. See how your memory is from grade 10. And remember the symbol? The symbol for rational is a capital Q. The symbol, the mathematical symbol for irrational is a capital Q with a line over the top of it. That means irrational. So if you see those symbols, those are the symbols that mathematically mean rational and irrational. Okay, so that's the first thing I wanted to look at. The next thing I want to look at before we get into our application problems, I think I got a couple examples here. So this is where, so you don't have a picture in front of you, and I just say, find the discriminant of each of these. Well, the first thing I got to do to make sure you're finding the correct discriminant is these have to be equal to 0. This one's not. So I'd have to do a quick little maneuver here and say, well, 9n squared, take away 3n. I'm going to add 10, so it's going to be plus 2 equals 0. And now I'd find the discriminant. So the discriminant is b squared, subtract 4 times a times c. So I can look here, and you don't even have to know what the exact answer is. You just need to know whether it's positive, negative, or 0. We'll actually figure it out. So I get 72. 9 take away 72, so that's a negative 63. So as soon as I see a negative value for the value under the square root sign, I know that there are no real solutions. Now up here in the descriptor, it wanted us to say the number of real and imaginary. So there's no real solutions, but there'd be 2 imaginary solutions. And the only way you'll ever get imaginary solutions is if the discriminant is negative. Any other situation, there are no imaginary solutions. Let's try another one here. Let's take this one. So let's set it equal to 0. 4a squared, subtract a to 8a plus 4, make that equal 0. One thing you can do here, I noticed in this one, notice how these are all divisible by 4. Because it's an equation, now you can't do this with expressions, but you can do it with an equation. You can divide these all by 4, because as long as you divide the right side by 4 as well, it's still going to be equal. And the right side being 0, 0 divided by 4 won't switch on you, it'll stay 0. So what that does, you say, well, why would I do that? What's the benefit? The benefit is it makes the numbers smaller, so that now when I go to do the discriminant, the numbers that I'm going to have to calculate will be easier for me to do. So let's figure out the discriminant. B squared, so B is negative 2, there's B squared, subtract 4, A is 1, and C is 1. So this is going to give me 4 take away 4, I'm going to get 0 as my discriminant. So if the discriminant is 0, you're only going to get 1, and it's going to be a real solution, meaning it's going to be found in the real number system. Let's see here. Let's try this one down here. So I'm going to have negative x squared, take away 6x, take away 9 equals 0. Now I talked to you about this in one of my earlier videos. I never like working with a negative in front of my x squared term. I'm just going to multiply all these by negative 1, both sides of the equation. Right? And remember, when the right side is a 0, it won't switch on us. So I'm going to get x squared plus 6x plus 9 equals 0. Do a quick check on my discriminant. My discriminant is b squared, subtract 4 times a times c. My discriminant is going to be 0, so that's the same as the one I just did up above. One real solution. Try to find one here where I get this one should be good. Let's go negative 9b squared plus 8b minus 8 equals 0. I don't want a negative there, so I'm going to go 9b squared, take away 8b plus 8 equals 0. Just multiplied everything, both sides of the equation by a negative 1. And now let's find the discriminant. So the discriminant is b squared. So b squared is 64. Subtract 4 times 9 times 8. It's going to be some negative number. Again, I don't care what it is. It's negative. As soon as you get a negative value here, that means you have 2 non-real or imaginary solutions. So this must be the one. That one doesn't look like it's going to either. Try this one. I'm going to move everything. Let's go everything to the right. So 0 equals 2x squared plus 8x. Add 14. That would be a plus 8. Let's see here. Everything will divide by 2. So 0 will give me x squared plus 4x plus 4. So the discriminant would be b squared. Subtract 4 times a is 1, times c, which is 4. My discriminant is 0, same as these ones down here. I was hoping to find one of them that would have given me a value of some positive value. Let's suppose, let's do one that I know will work. Let's take let's suppose I had this quadratic. Okay, so we'll look at this example just to show you an example where the discriminant is some positive number. So those other ones all have 0 or negative. Let's quickly find the discriminant of this one. So the discriminant would be b squared. There's b squared. Subtract 4 multiplied by the a value multiplied by the c value. Now negative is going to make this a positive, so it's going to be 4 plus 12 times 8 is 96. 96 and 4 is 100. All right, so this time that tells me that there are two distinct roots, distinct real, meaning different. So there's no imaginary roots. And furthermore, notice that this is a perfect square. I set that up on purpose. I made sure it was a quadratic that would factor. That tells me that it is a factorable quadratic, which tells me that the solutions are also rational numbers. Right, remember, if it's any other number besides a perfect square, they would have been irrational solutions. Okay, so that's a quick look at what they refer to as the discriminant and how to use it to find the types of solutions or the nature of the roots of a quadratic equation. Next thing we're going to look at is how to create a quadratic from the solutions. Meaning, suppose I wanted a quadratic to have a certain pair of x-intercepts, then I can make the equation have those x-intercepts. So it says, Tori says she solved the quadratic equation by graphing. She says the roots were this. Can you figure out what was the equation she must have solved that gave her those answers? Now, I just want you to look at something real quick. Let's suppose I had, let's take an easy quadratic, x squared minus x subtract 6 equals 0. And I got you to say, and I said, solve that for me. Well, it's a nice simple trinomial that factors, so we would probably, the most efficient way is go x subtract 3, x plus 2 equals 0, and I would get the answers x equals 3, x equals negative 2. So to get that solution, I essentially started here, and I worked my way down. What I'm asking you to do now is, could you take the knowledge you've acquired, and could you start here and work your way back up from the answers to the quadratic that gave those answers? So think about it now as if I erased this part of the question, so you didn't know this anymore. If you just knew this, could you work your way back up? Well, I'd hope you'd say yes. It's not like I'm teaching you anything new. It's taking acquired knowledge and using it in a sort of different strategy. So my brain would have to say, well, the only way I can get x equals 3 as an answer is if x minus 3 must have been one of the factors. The only way I could get negative 2 as an answer would have been if x plus 2 was equal to 0. So all you got to think about is you're essentially moving everything backwards. So instead of having your equals 2 here, just move it back over where it came from. So x plus 2 equals 0. X take away 3 equals 0. Well, then the quadratic is created by the product of these two factors. So it must have been x subtract 3 multiplied by x plus 2 equals 0. And then you just expand it out. X multiplied by x times 2, negative 3 times x, and negative 3 times 2 is a negative 6. Collect your terms in the middle, x squared minus x minus 6. That must have been the quadratic that gave me those answers. Now, back to the question at hand then. So she said that these were her answers. X equals negative 5 was one of the roots, and x equals 7 was the other root. So what I said is if I know these, I can figure out what the factors were that must have gave me those answers. Just move things back where they came from. Say, well, this must have been x plus 5 equals 0. And this one must have been x take away 7 equals 0. And the only way I would have got those two single linear equations would have been if the two factors that multiplied together were x plus 5 and x subtract 7 equals 0. Expand. X squared take away 7x plus 5x subtract 35 equals 0. There you have it. So I know that this quadratic would give me those solutions. So that's kind of a neat little trick for a teacher to know, because if I'm making up a question for an exam or a test, and I say, I'd like the students to get a certain set of answers. Well, I can just write out what I want the answers to be, and then very quickly figure out what was the quadratic that would give them those answers, and then I can kind of work backwards from there. Okay, so we're going to do a few examples of that, and as you can probably guess, they'll get more complicated. That's a pretty easy starting point. So this one says the x-intercepts of the graph of a quadratic are x equals 3 and x equals negative 2.5. Write a quadratic equation that has these roots. X take away 3 must equal 0. X plus 2.5 must equal 0. Then the product of these two would give you a quadratic that has those answers. X subtract 3 multiplied by x plus 2.5 equals 0. X times x is x squared plus 2.5 x, take away 3x, subtract 7.5 equals 0. X squared minus a half of x, subtract 7.5 equals 0. Now, I didn't get into it on the last one, but this is a possible solution. In theory, every single person in the course could have a different answer here. Now, most would probably arrive at the same starting one, but there's nothing, when you have an equation, an equal sign, especially when it equals 0, there's absolutely nothing to stop us from multiplying this equation through by any number I want and it still being correct. So for example, you may say, I don't really like those fractions in there. I could say, sure, well, let's fix that then. Why don't we just double everything? If you go across and double both sides of the equal sign, you'll have 2x squared minus 1x, take away 15, equals 0. This would be right, so would this. For whatever reason, student B would say, oh yeah, I thought maybe if I just multiplied by 10 it'd be easier. Sure, why not? 10, x squared, subtract 5x, subtract 75, equals 0. There's another correct answer. So you can kind of see where I'm going with that in theory, I could multiply by any possible number and I'll get a quadratic that may be different than this one, but it would give me the same solutions. When you multiply through a quadratic by a constant, it doesn't change the values of your zeros. They're still going to be the same. So the reason I mention that is that I might come up with this equation. Student B sitting next to me might have had this equation, but we're still both right. So when you look in the back of the textbook or an answer key for one of these, they're going to give you a solution. There could be more than that one solution in this type of question. All right, now I'll get a few more of these. So I want a quadratic equation that has these two answers. So that's pretty easy to do. X equals negative 7, x equals 4. So now we're going to move those back over. So it's going to be x plus 7 equals 0. X take away 4 must have equaled 0. So now then you multiply these together. You're going to get x squared, take away 4x, plus 7x, subtract 28 is 0. X squared plus 3x minus 28 would have to be 0. This quadratic would have those solutions. So now all of a sudden, oh no, fractions. Doesn't matter, it's just as easy. X equals negative 5 over 2. X equals 2/3. Now remember what our strategy was here. Our strategy, now it was easier here because it was just a single number. Our strategy was to move everything back over here and make it equal 0 to get the linear factors that gave those solutions. Not going to change here. So, but it's going to be 2 steps instead of 1. I need to get rid of the 2 on the bottom. So what I'm going to do first is double both sides. So now I'm down to 2x. That gets rid of the 2. 2x equals negative 5. Move that over. 2x plus 5 equals 0. There's the linear that would give you that solution. Now, once you get the hang of that, you can do that a little bit quicker. You can probably do it in 1 step. You don't have to show all this work. I'm going to multiply by 3. Right, that'll get rid of that. But then I'm going to have to move the 2 over. So 3x take away 2 equals 0 would give you 2/3 as an answer. Then take your 2 linear equations and multiply them together to get your quadratic. 2x plus 5. You need to multiply it by 3x subtract 2. 6x squared. Take away 4x plus 15x. Subtract 10 equals 0. Collect those middle 2 together. And there you have it. That quadratic would have those solutions. All right, so at this point, most students are saying, okay, I get the hang of that. That's not too bad. I think I'm going to manage. And then I'll say, all right, are you up for a challenge now? What if you get ugly answers? You want the students to get ugly answers. You want their answers to be like this. X equals negative 5 plus or minus root 3. Well, the good news is it's probably, once you see the little strategy I'm going to show you here, it's probably even easier for these ones than the ones that we just did. And I'll show you how. The first instinct, a lot of times, so if we were in a classroom environment going through this, I would just put these up and say, oh, go ahead and see if you can find a quadratic. And most students are inclined to try and use the quadratic formula and say, well, that's the only way you're going to get answers like this is if you're doing the quadratic formula. And you are right. However, there is an easier way to do it than trying to mold it into the quadratic formula. And that's what I'm going to show you. Basically, what I'm going to show you is what I just did with those last ones. We're going to move everything from the right back over to the left and get it equal to 0. But watch what happens. But start with this. So take your negative 5. You're going to leave your plus or minus term by itself. So you're going to move that negative 5 over, and you're going to get x plus 5. So then we say here, yeah, I got 2 different things here. How am I going to deal with that? Well, here's the good news. I have this radical that I want to get rid of. So what I'm going to do is put that whole right side in brackets. I'm going to put squared. And the reason I'm going to be allowed to do that is because whether it's a positive or a negative, when you square it, you're going to get the same answer. So it doesn't matter. Now, whatever you do to the right side, you have to do the same to the left side. Binomial squared. 3 steps to square it. So square the first, multiply and double, square your second one. Now this gets really easy. Plus or minus, guaranteed it's positive because you're squaring it. And when you square a square root, you just get that number, move that over, x squared plus 10x plus 22 equals 0. There's the quadratic that would have those ugly answers. Okay, same thing here. X equals negative 3 plus or minus 5 radical 2 over 4. So our goal is to get everything to the left side, make it equal 0. This one's got an extra step because of the 4 on the bottom. So the first thing you'd have to do is multiply both sides by 4. That's gone. So then you're going to move your negative 3 over. It's going to become plus 3. You want to isolate your plus or minus with the radical in it. Then we square both sides. Square the first. Multiply, so that's 12x, and double it. That's plus 24x. Square your plus 3. There's your 3-step rule. Plus or minus, guaranteed it's going to be positive because we're squaring it. Now, if there's a coefficient, you got to square that 5. So that's 25. Then square your radical. So you're going to multiply those together. That's going to be a 50 over here now. We're going to move that to this side. 16x squared plus 24x, 9 minus 50 is a negative 41 equals 0. So this ugly old quadratic will give you these answers here. All right, so even though we had these irrational solutions, it's really not that difficult to build a quadratic that would have those solutions. It's a slightly different strategy than I used in the last couple of slides, but it works very nicely as well. Okay, so now the last thing we have left to do is we're just going to take everything we've learned about quadratics. We're going to be presented with a problem, and we're going to figure out how to deal with it. So we're not going to teach you anything new other than take the knowledge you have and use it to solve a problem. So now remember, you should, as much as possible, actively be participating, not just sitting watching the videos. You want to pause and try the questions as the videos are kind of unfolding here. All right, so this one's talking about someone standing on top of a 1,680 foot tall building. They throw a small object up. At every second, they measure the distance of the object from the ground. Exactly t seconds after we throw the object, its height measured in feet. So this is the function that gives you the height of the object. So you can see that it has got a negative stretch factor, so it opens down. And it's definitely a quadratic, so it's going to follow a parabola. So part A says find h of 3. That means h of 3 function notation from grade 10. That means replace t with 3 to get the height at the 3 second mark. So part A, h of 3 is negative 16. Replace t with 3. And that's going to give us 2,304. Now, this question has units, context, so they're talking feet. Think about what happened. They were on the top of a building 1,680 feet above the ground. They threw a small object up in the air, and then it came back down. So the height would increase till it reached its highest point, and then it would drop till it hit 0. So if you modeled that on a graph, it'd be this type of scenario. So we just figured out that at the 3 second mark, it's still up above where they threw it. So it's up at 2,304 feet. It says, how much does the object travel during the 2 seconds between 5 and 7 seconds? Well, to answer that, what we're going to have to do is figure out where was it at 5 seconds and where was it at 7 seconds, and then hopefully that will help us map out how far it traveled. So let's try that. So we're basically just going to find h at 5. So put 5 in for t. And then we're going to find h at 7. So put 7 in for t. So I'll just do those. I'm not going to show it all so everyone understand. We're just going to fill in, substitute 5 for t, get our answer. Substitute 7 for t, get our answer, and see if that helps us to answer this question. So let's do that calculation. Okay, so there's our two values. So at the 5 second mark, it was at 2,560 feet above the ground. And then at the 7 second mark, it's at 2,688 feet above the ground. So the question was how far to travel in that 2 second span. So we're just going to get the difference between those two. Take the 2,688 and subtract 2,560. And the object would have traveled, let's see what I get here, 688, subtract 2560, 128 feet. Part C, how long does it take for the object to reach a height of 2,640 feet? So this time they're telling me the height, which should be the left side. The left side of this equation represents the height of the object at any time t. So to do part C, they want us to solve this equation. 2640, so your height equals negative 16t squared plus 256t plus 1680. Oops, one, that's not working there. Run that around. 1600. Note the edge here. Anyway, that should be 16,880. Let me put it in there. Alright, so this is the equation we're trying to solve. We want the height, which was the left side of that quadratic function, to equal, this was our right side. Let's make this equal to 0 to solve, and then we'll see what strategy we're going to use to solve this. We have to solve for t. What times does it take to get to this height? Let's move, because I got a negative here, I'm going to move all of this stuff to the left. That'll give me 16t squared, subtract 256t. Now I need 2640 minus 1680. That'll give me 960. That would equal 0. I would first thing do here, check and see if maybe these will all divide by 16. That will really make our life a lot easier. If it does, let's try it. I think it does actually. So 256 divided by 16 is 16, and 960 divided by 16 is 60. So perfect. So I'm going to divide left side and the right side all by 16. That will give me t squared, subtract 16t plus 60 equals 0. Now we've got a nice simple trinomial that actually factors. Multiply to get positive 60, add to give negative 16, negative 10, negative 6. T take away 10, t subtract 6 is equal to 0. So t equals 10, or t equals 6. Now, what was the question? How long does it take for the object to reach a height of 2640? Now, you say, why are we getting two answers? I want you to think about what happened. They were on a building that was 1,680 feet high. They threw it up in the air, and it came back down. 2,640 feet was up here somewhere. So let's suppose this was 2,640 feet. So when the object went up, the vertex must be above 2,640. It went up to its highest point, and then it came back down. So it would have reached 2,640 feet at 6 seconds for the first time, went up to its highest point, and then started to fall, and then passed 2,640 feet again at the 10-second mark. That's why you're getting these two times that make sense. How long does it take that to read? So based on the wording of the question, I think it's asking for the first time. So let's say it took 6 seconds for the first time. But we do realize it actually hit that height again on the way down at the 10-second mark. So that's kind of an example of understanding how to solve. When you solve, how to interpret, why did I get two answers? Oh, okay, that all makes sense based on what's going on in the question. How long does it take for the object to hit the ground? Well, the ground, all we're going to do is change this number to 0. Okay, so it's going to be another quadratic equation. Part D, 0 equals negative 16t squared plus 256t plus 1,680. Now again, I'm going to check so I know that 256 will divide by 16. It's 16. Let's try 1680. That goes evenly, 105. Okay, so I'm going to divide everything by, how about we divide everything by negative 16? Again, that won't change over here, but it'll switch this to a positive for us. Zero equals t squared, subtract 16t minus 105. Now at this point, I look this over. Do you remember I mentioned in our video on solving that give it 10 seconds, 15 seconds. Can you think of two numbers that multiply to give negative 105? And when you add those two numbers, you get negative 16. And now maybe you do. Maybe you've tried a couple divisions on your calculator. It ends in 5, so try dividing by 5, try dividing by 15. Might work. But let's pretend that I got here and I couldn't figure out any factors. And maybe it doesn't factor. I really don't know. What I'm going to do this time instead is I'm going to rely on the quadratic formula. So t equals. So t is taking the place of your x. So instead of x equals, it's t equals negative b plus or minus the square root of b squared subtract 4 times a times c. All of that divided by twice the a value. 16 plus or minus. Now the next thing I got to figure out is what's this equal. So I've got 16 squared so that gave me 676. That's the value underneath the square root, which we now know is referred to as the discriminant. Let's see, is 676 a perfect square? It is a perfect square. So 26, 16 plus or minus 26. So what do I now know? I now know that it would have factored, which is fine. I'm pretty much at the answers now, so let's get our two answers. 16, subtract 26. That's going to give me a negative 10 over 2. T is negative 5. Don't like that. And then I'll do the other one. 16 plus 26, so that's 42 over 2. T is 21. So therefore, I can't, because of this question having the context, t representing time, I can't have a negative time. That's called an inadmissible root based on the context of the problem. This must be your answer. T equals 21 seconds. So it takes 21 seconds for that object to go up in the air to hit its highest point, fall, and then eventually hit the ground. Which tells me that for any of you that did factor this, 21 and 5 would have been your factors. T minus 21 and t plus 5 would have given you your 0. That would have given you those two answers. Okay, but that's the value in showing you that your quadratic formula will certainly suffice if you don't see your factors right away. Okay, I think there's a couple of extra questions here that I added on. So then it says, what was the maximum height reached by the object? This takes us back to our first part of the unit on quadratic functions. As soon as you see maximum height, hopefully your brain is thinking, I need to know the vertex. So the height of this object, I'm just going to try and squeeze it here so I can see it, was negative 16t squared plus 256t plus 1680. So what we need to do is complete the square. Now, what students will do wrong here sometimes is say, oh, these all divide by negative 16. I'm going to divide by negative 16. You can't do that here. It's not equal to 0 or equal to 10 or equal to 50. It's a function. So in this case, E here, I just complete the square like I would have back in the first part of this unit. Take out your negative 16, t squared minus 16t plus, leave room to complete the square, plus 1680. Half of 16 is 8. 8 squared is 64. 64 times negative 16 is a negative 1024, which means I'm going to have to add 1024 at the end. I'll just squish it down here. Don't have room right beside it. And now let's go to vertex form. So vertex form would be negative 16, square root of the first, sine of the middle, square root of the last one, all squared. 1680 plus 1024 will be 2680, 2704. So your vertex is at 8, 2704. Remember when it had context, we interpret that. So what does this mean? Well, instead of where the x usually is, this is your t, that's your time. This is your height, where your y usually is. Question says, what is the maximum height? So the answer to part E is 2,704 feet. The answer to F, work's already done for it. It says, how long did it take to reach the maximum height? Well, that's the time when you're at that vertex, which would be 8 seconds. There you have it. Real nice example of a question. There's a test type question where it takes a lot of things we talked about in the unit and puts it in together with some nice context where your quadratic has some meaning. All right, on we go now to a couple situations where the function's not given, so you're going to have to create the quadratic function. So we notice no quadratic given in the question. So we're going to read, interpret, see what they're telling us here. So we get divers. They're performing dives from opposite sides of a platform. That's 10 meters high. The two divers reach their maximum height of 0.6 meters above the platform after 0.35 of a second. How long did it take them to reach the water? Well, if we kind of map out what's going on here. Our platform is 10 meters in the air. They go up and then end up down in the water. So they basically gave us this point right here, the highest point. It was 0.6 meters above the platform. So that doesn't mean it's, because the platform's 10 meters, so this must be the ordered pair. 10.6, comma, and then, oh, I got that backwards, sorry. The height, that's the y value. So let's think graph here. So they started at 10. At 0.35 of a second, they're at the highest point. Back down like so. So this point would have been 0.35, 10.6. This point over here would be 0, 10. So we need to come up with a quadratic. And then the question is, what is the question? How long did it take them to reach the water? So that would be when the height is 0. So essentially I've got to figure out when is the height 0. Well, let's make a height function. So the height would equal, remember now, we do y equals a x subtract h squared plus k. So we've done this kind of thing before where we build a quadratic to model a situation. So height equals, I don't know the stretch factor yet, x minus the x coordinate of your vertex is 0.35 squared, and the y value is plus 10.6. So then what we can do is fill in another point. So this is your other point, this is your x and your y, or in this case your time and your height. And let's put in a height of 10 equals a the x, or the time, I guess in this case would be 0. Subtract 0.35 squared plus 10.6. Now I'm going to solve for my stretch factor. So I'm going to subtract 10.6. I'll get negative 0.6 is equal to a. I'm going to square 0.35. That gives me 0.1225. 5. Divide both sides by that. 0.1225. And we will get a stretch factor of 0.6. 4.89, so it's, remember, if it doesn't go evenly, we're going to carry 3 decimals. 4.8979, that would round off to 898. So the height of the divers, that would be a negative, sorry, because it's negative divided by positive. Negative would make sense, quadratic opens down. Negative 4.898 multiplied by x, subtract 0.35 squared plus 10.6. Now, question is, when does the diver hit the water? That would mean figure out when their height is 0. Now for x, x is the number along here, which is t. I should probably switch that out. Let's call it time instead of just generic x. So in this question, it means time. So time minus 0.35 squared plus 10.6. Because it's in vertex form, why don't we just rearrange it and take the square root of both sides? Remember, that was one of our shortcuts that we could use here. So it's going to be negative 10.6 equals negative 4.898 t minus 0.35 squared. Divide both sides by negative 4.898. So 10.6 divided by 4.898. I get 2.164. 2.164 equals t subtract 0.35 squared. Take the square root of both sides. Remember, you're going to get plus or minus here. So, square root. My answer is 1.471. Squaring this, or square rooting something squared will just give me this. We're going to move that over there. So my times will be 0.35 plus or minus 1.471. It can't be the subtract because that would give me a negative time, so it must be 0.35 plus 1.471, giving me a time of 1.821 seconds. There's how long it would take them to hit the water. It's a neat question. Took some measurements and times, turned it into a quadratic function, used that quadratic function to answer a problem. Prime example of an application of a quadratic. We saw this type of question when we did maximizing and minimizing revenues and that type of thing. This one's a little different in that kind of lays out, you've got they rent 750 video games if they charge $450. If they raise the rental they're trying to increase their revenue to $7,000 per month. But what they realize is that if they put the price up, the rental price by $1, then they're going to lose 30 rentals. So that's kind of the function they built for it. They did it for you down here. And basically what they want to know is it possible for the owners to increase the rental rate to generate $7,000 per month? So basically, could their revenue be $7,000? Let's find out. This one's a little bit easier because we don't have to build the function. They did it for us. But we still got to do the work to solve the equation. So if this was equal to 7,000, well, we're going to have to expand this out. So I'm going to expand this out. All right, so I just went and did a couple of calculations to save us some time here. So when I multiplied this all out, I got this on the left side. Then I moved my 7,000 over and I arrived at this quadratic. So the question is it possible to get a value for P being a price increase, so that this actually works out? So we're going to try and solve it and see what happens. I don't like the looks of these numbers right away. I'm going to go quadratic formula. They're not going to divide by 30, so it's still going to be a hard try. You could probably divide everything by 5, 15 maybe. Get the numbers a bit smaller. But I'm just going to leave it like it is and go right. Actually, maybe the one thing I will do is, because I'm using the quadratic formula, I guess it doesn't matter. I'm just going to go right quadratic formula. P equals negative b plus or minus b squared subtract 4 multiplied by a multiplied by c divided by twice a. And I'm going to see what I get here. So negative 615 plus or minus. So I'm going to go do that calculation now. All right, so after putting that on my calculator, this is what I came up with, which tells me this is not possible, meaning there's no possible way, so there's no solutions, because you got a negative underneath your square root sign. It would be impossible to somehow come up with $7,000 per month under the conditions outlined in the question. And that's so me being able to interpret what happened here and say, well, okay, I understand. That means this is impossible. Oh, we're going to skip those for now. Okay, a few more. This one wants us to find x on the indicated figure below. Round your answer to the nearest thousandth. Key here is the right angle in the corner, which means this diagram represents a right angle triangle, which means it must follow Pythagoras' theorem. So that means if I square one of the heights, or the legs, and then I square the other leg, I have to get the hypotenuse squared. Every right triangle must satisfy Pythagoras' theorem. Now let's turn this into a quadratic that we can manage. So I square this one. Make sure you square the 2 here, so it's 4x squared. 3-step rule, square the first, multiply and double, square the last one. Set it equal to 0. Let's take everything left, so I got 5x squared. Take away that x squared, I'm going to get 4x squared plus 8x. Subtract 16 equals 0. Everything will clearly divide by 4, both sides of the equal sign, so I get x squared plus 2x. Subtract 4 equals 0. No way that it will factor. Therefore, we're going to have to go quadratic formula. It did say in the question nearest thousandth. That means 3 decimal places. Well, let's go formula. X equals negative b plus or minus square root b squared, subtract 4 multiplied by the a value multiplied by the c value divided by twice the a value, 2 times 1. We will get the following answers. X equals negative 2 plus or minus That's the square root of 20 over 2. So x will be -2 plus or minus square root of 20. It wants to remember the nearest thousandth, so carry 3 decimal places. Square root of 20 is 4.472. Divide that by 2. All right, so back. I apologize. I keep having some technical issues where my software's freezing up on me, so I'm just back to where we were. The work all above is gone, but I had to restart. So here we were. This is what we were talking about, and I got these 2 possible answers. Now, based on the question, x being the length of this side of the diagram, that means this answer is inadmissible. I can't have a negative length of a diagram. Therefore, the answer here, find x, would be 1.236. All right, so there's using Pythagoras' theorem as kind of a way to generate a quadratic equation. Let's have a look at this one. Talking about a rectangle, it says the length of a rectangle is 2 meters longer than the width. The area is 10 square meters. What are the length and the width? Now, this one's pretty straightforward. I like drawing a diagram for these type of questions. So they say the length is 2 more than the width. It's the width plus 2. This is the width. The area is 10. Well, area is length times width. So W multiplied by W plus 2 has to give me 10. W squared plus 2W. Bring your 10 over. Multiply to get -10, add to give 2. There are no factors. We're going to have to go quadratic formula. W equals -b plus or minus square root b squared 4 times a times c divided by twice a, -2 plus or minus the square root of 44. This will be positive because of the 2 negatives here, so it's 44 over 2. All right, so let's see what I get for values here. All right, so after my calculations, I came up with W could be 2.317, or W could be -4.317. Based on the context of the problem, W being the width of the rectangle, that is not a possible answer. Therefore, the answer to their question is, I just want to get units on it. Anytime there's context and units, your answer should have units. What are the length and the width? So the width is 2.317 meters, and the length is 2 more than that, 4.317 meters. Okay, let's see what we got next. Talking about a parallelogram, so parallelogram, let's draw a picture. The base of the parallelogram is 6 inches longer than its height. So let's suppose this is the height. The base is the height plus 6. The area of the parallelogram is 10 square inches. So it's basically the exact same thing as the last one. The area of the parallelogram is base times height. Right, base multiplied by the height. So in the context of this question, I want the area to be 10. The base and the height are h and h plus 6. H squared plus 6h minus 10 equals 0. Solve for h. I'm not going to show the rest of that. You guys can do that, no problem. Olin's garden is 5 feet wide and 8 feet long. So it's 5 and 8. He bought enough seed to plant 100 square feet in okra. If he wants to increase the width and the length by the same amount, so he's going to make this bigger. Make it bigger. I didn't draw a great picture, but he's going to do that by increasing it, the length and the width, by the same amount. Actually, maybe let's try that again. I don't think that's what they mean. So the diagram should go to, the new garden is going to look like this, where it's going to go this way by some amount, this way. Didn't say on both sides. So this side would become 8, what it used to be, plus that new addition. This would be 5 plus the new addition. Now the new garden is going to be able to accommodate 100 square feet, meaning that times that should give me 100. 8 plus x multiplied by 5 plus x would have to be the area that I want, which is 100. This gives me 40 plus 8x plus 5x, that's plus 13x plus x squared is 100. Let's get it in a manageable form. X squared plus 13x minus 60 equals 0. Negative 60 and 13. 10 and 6, 12 and 5. Doesn't look like it's going to factor. X equals negative b plus or minus square root b squared. Subtract 4a c. Everything divided by twice a. X equals negative 13 plus or minus. Do a calculation here again. Alright, so I put this in my calculator here. I got 409. I took the square root of 409. I got that. And now I'm going to get my two possible values for x. Well, one of the answers is going to be negative 13. Take away 20.24 divided by 2, which is going to give me a negative answer. However, based on the context of this problem, x is how much extra I'm going to add on to my lengths. I can't use a negative value, so that one doesn't work. Let's do the other one then. So negative 13. I'm going to add 20.224, and then I'm going to divide by 2, and that should give me how much we're going to add on to the length and the width. So take away 13, and then divide that by 2. So we're going to add it with 3.612 feet. 3.612. Question was in feet, I believe. I think that's what I was asked. Let me see. It said, then what should the increase be? Yes, the increase should be. So they should add an extra 3.612 feet to both the length and the width if they want the area of the new garden to be 100. All right, last type of question we're going to look at are ones involving speeds and times and distances. I'm just going to show you, I'd like to show you these ones too because there's a nice little way to do these questions using what's called a chart approach. So I'm going to make a chart, and I'm going to put across the top of this chart, I'm going to put distance, speed, and time. And I'm going to make 2 rows in my chart. So in this case, one of the rows will be for Gladys, about her commute to work, and the other one will be Bonita. We're talking here about miles for the distance. I'm just going to put units here so we know what units are in. These are in miles. The speeds are in miles per hour, and the times are going to be in hours. So those are the units, so I'm not going to put them on my values here. All right. One of these columns will always be able to be filled in with numerical values. They're given in the question. You're just going to read and search and find them. Bonita drives 40 miles and averages 9 miles per hour more than Gladys. Gladys drives 50 miles. There's 2 numbers that I know for sure. Bonita travels 40 miles and Gladys drives 50 miles. Now you got to read these questions. So students will see here 9 miles per hour, stop reading, and they'll put 9 miles per hour down as Gladys's speed. That's not what it says. It says that she averages 9 miles per hour more than Gladys. Well, I don't know what Gladys's speed is, but I do know that Benita's is 9 more. Now, at this point, what you're going to do is rely upon some basic science knowledge that the distance is equal to always the speed multiplied by the time. And once you've got 2 columns filled in the chart, stop reading the question for a moment, and you're going to use this formula to get the 3rd column in your chart. So in this case, the time will be the distance divided by the speed. So the time will be the distance, 50 divided by x. And this one will be 40 divided by x plus 9. Then that column that you fill in with the formula, there's some information about it in here that will allow you to turn this into an equation. This is the key right here. She's on the road, so Gladys is on the road 1/2 hour longer than Benita. That means her time driving is 1/2 of an hour more than Benita. So Benita's time, and then I'm going to make an equation here, so let me think now. Gladys drives 1/2 hour longer. So that means that if we took Gladys's time, 50 over x, and we took away 1/2 an hour from it, we would get to this type of an equation. Now, at this point, we've generated an equation here that is probably a little bit more complicated than we're ready to deal with right now. I'm not really too concerned about this. We'll get to it in our unit on rational expressions. What I'm concerned about now is setting up these charts, showing you how to do this. At this point, this involves a little bit more rational expression work than we've experienced to solve. But you'd have to get rid of the fractions, turn it into a quadratic, and solve. As I said, we'll get to that in the next unit. But I'm concerned with you setting up the chart, using the chart to build an equation like I just did. Okay, we'll do one more of those. So again, I'm not going to quite finish that question. I'm just showing you kind of the layout of how to set one of these up. All right, this one, we're talking about going upstream to do some fishing and then coming downstream because of the current. In these questions about currents, you're going to let x represent the speed of the current. And you're still going to do a chart. So we're going to go upstream, and then we're going to come downstream. We're going to make this into a distance, speed, and time chart. So distance, speed, time. My units are in miles. My speeds, they're talking about miles per hour. Now you got to be careful here. If you're in miles and miles per hour, you want your time to be in hours. But I noticed this question has my time in minutes. I'll deal with that when I need to. So you do got to watch for units. Okay, so let's look for one column that we can fill in for sure with numbers. So if we think about this, we got a stream, like so. And let's suppose the water's running down this way. So this person got in their boat, and they went upstream, they went fishing, and then they came downstream. Well, however far they went up, they had to travel the same distance to come back. So the 6 miles upstream would have to be the same as their trip downstream. Their speeds. Oh, sorry, I messed this up. X isn't the current speed. They tell us the current speed. X is the speed of the boat in still water. So X represents not current speed, their boat speed. Speed of the boat. And it wouldn't make sense to let it be X, the speed of the current, because they told me the speed of the current. This is what I do know. However fast I was going upstream, because the current's pushing against me, it's going to take the speed of my boat and it's going to take 2 miles per hour off of it because of the current. But then when you turn around and you come back downstream, now the current's pushing at the back of the boat. It's going to make the boat go whatever it's traveling plus 2 more. Remember, once you've got 2 columns, get your third by taking distance. Use your formula. Time is distance over speed. Distance over speed. And what I know is it took 20 minutes longer to get there, making sense, right? Going against the current is going to take longer. But the one thing you got to do is do a conversion. Well, let's say, what's 20 minutes in hours? Well, what I know is that there's 60 minutes in 1 hour, which means I've got 20 over 60, or 1/3 of an hour. So it takes 1/3 of an hour more to go upstream. So if we took their time to travel upstream, and we took 1/3 of an hour off of it, it should then be the same time it took to travel downstream. So that's the reading and interpreting and setting up the chart part of the question. Now, unfortunately, it generated a rational expression, which upon us completing our unit on rational expressions, we'll be much more better equipped to deal with this. But right now, I don't want to throw you in over your heads and get you swamped into something you don't need to deal with yet. I'm not saying you won't at the end of the course be able to solve this. Just right now, we don't have the skill set to do this. But this is the important part. How do I take a distance speed situation and manage it using a chart? Use my chart to then generate an equation. All right, that wraps up your unit on quadratic functions and equations. I'll give you some application questions from your textbook, and I think I have a handout as well that you can use and try and get some experience and confidence dealing with this material. After we do that, we'll have a unit review, and we'll be ready for a kind of a final assessment on all of the information on quadratics. As always, best of luck. Reach out if you have any problems.